we are going to start today the Bessel function. Bessel differential equation. Bessel differential equation. So these differential equations, already we have seen algebraic differential equations are very important, especially in the study of quantum mechanics. And similarly, Bessel differential equation also is very important in the study of wave equations. So especially in physics, we will be dealing these wave equations, and these equations exactly they resemble with Bessel differential equations. These Bessel differential equations is given by x squared y double prime plus x y prime plus x squared minus y squared into y equal to. So the equations which is of this type is known as Bessel differential equation. So this equation is known as Bessel differential equation. And the solution of this equation is very important thing. So it will appear in the examination. So the solution of this differential equation is known as Bessel function. So the solution of this differential equation is known as Bessel function. Bessel function of order say n, because it is the solution of this kind of differential equations is known as Bessel function of order n. So there will be Bessel first order, there will be Bessel second order. So as we have seen earlier, algebraic differential equation. So we have polynomials of first kind and polynomials of second kind. So similarly we have Bessel function of first kind and Bessel function of second kind. Okay. So first kind and second kind both are known as linear combination of equations. So we have solutions we have solutions which are nothing but the linear combination of two or more functions. So totally put together we have solutions. So as usual, so we are going to solve this Bessel differential equation by means of power series. Ascending power, as usual, the same method we are going to follow power series. So maybe ascending order as well as descending order. So we have the solution, we are going to assume the solution in terms of power series. So this will be nothing but ak x to the power k. Last time x to the power k. But this time we are going to find k plus r. So k equals 0 to. So as usual, you just differentiate once. So that will give you k equal to 0 to infinity k plus r into x k plus r minus. So similarly, y double prime equals to k equal to 0 to infinity k. Correct? So here must be 1 to infinity. Okay. For the time being we will have, okay, you are right. So 1 to infinity will wait for us. So this must be what? K plus r plus k plus r minus 1. Yes, k plus r minus 2. So just to substitute this solution is here in the differential equation. So this must be what? Equation 2, this must be equation 3, and this must be equation 4. So you are going to substitute all these equations, all these solutions here somewhere in equation 1. So we will get ak, okay, k plus r minus 1, x to the power k plus r. Okay, is it clear? Okay, plus summation AK K plus R K plus R x to the power. Okay, this section will get cancelled. So plus summation AK x to the power, come on, x to the power K plus R plus 2. Yeah. K plus R plus 2. Is it clear? Everybody. So next equation will be minus m square AK x to the power K plus R. This is equal to in all summation we just find out we finding out only in terms of K series, not R series. So you can pull x to the power R out. Correct? So here summation stands from K stands from 0 to infinity. Here also K, here also K, and here also K. So here R is there. So you can put R out. So that will give you x to the power. Is it clear what I am saying? You pull x to the power R out. Okay? Because summation stands for only from K. Okay, only for K. So this becomes A plus R plus R minus 1 x to the power K. Okay? So now I have put x to the power R out. A plus R x to the power K. So similarly, we have AK x to the power K plus R K plus 2 minus m square AK x to the power K. Okay. Is it clear? First term there is a correction. Summation. So what I can do is these two terms. Look at this term and this term and this term. Okay. So because x to the power K is common, so all the three terms x to the power K is common. I can pull x to the power K out. One possibility is that. Okay. So we have x to the power R cannot be equal to 0. So this must be equal to 0. So I can remove x to the power R. Is it clear? Is it clear? So we have now AK K plus R K plus R minus 1 plus okay AK K plus R minus n square sigma AK. So I can pull x to the power K minus plus sigma AK x to the power K plus 2. So here I have pulled K to the x to the power K out. Okay. So here what I can do is, so here K equal to 0 to infinity as I said. So I am going to change as K minus 2 x to the power K. So this I can write this as K AK minus 2 x to the power K, which is equal to 0. So now this term K plus R is common. So I can pull K plus R out. So sigma AK K plus R. So this becomes K plus R minus 1 plus 1 minus n square. Is it clear? X to the power K. I have put K plus R common. I have taken. So K plus R, taken K plus R common. So remaining term will be K plus R minus 1. Here one term is there. So I have taken as plus 1. So this one and this one. Okay. Okay, is it clear what I am saying? Right? Very nice. in these two terms, so here these two terms, I pulled k plus r out. So this becomes k plus r. The remaining term will be k plus r minus 1. From last no issue. So I have taken k plus r out. So this becomes k plus r minus 1. Okay, so k plus r minus 1. The remaining term here already I have taken out. So remaining term will be plus 1. Minus n squared is this one. So yeah. Okay. So is this okay? So remaining term will be ak equals to h. So you have now sigma ak k plus r whole square minus l square, okay, h to the power k plus sigma k equal to 2 to infinity. I have changed this base h to the power k equal to 2. So now I take r equal to 0 first. Okay, now k equal to 0. If k equal to 0, the first term becomes a naught r square minus n square, then k equal to 1. Okay, so I can write this as k, substitute k equal to 1. So this becomes a1 1 plus r whole square minus 1. Okay, so here this becomes x. Okay, here x to the power 0, here x to the power 1. The remaining term will be here I have taken k equal to 0 and k equal to 1. Now k equal to 2, I can pull this term here inside. Is it clear what I am saying? Because already k base 2 is there. I can pull the rest of the terms in this term. So we have k equal to 0 term and k equal to 1 term. The next term will be k equal to 2 term. Already we have k equal to 2 term here. So I can combine these two and write. Is it clear what I am saying? So I can write k equal to 2 to infinity k plus r whole square minus n square. Okay, this term plus ak minus 2 sigma, of course we have x to the power k equal to 0. So this will be your common. Okay, so x to the power k is common. Even I can write x to the power k here. Okay, correct? Okay, I can write it. Is it correct? Is it clear? Okay. Now I can equate all the coefficients. Equate. Equating the coefficient. So I am going to equate the first coefficient. So you have a naught r square minus n square equal to 0. The first term will not be equal to 0. A naught is the first term. First term surely this will not be equal to 0. So a1 here it implies a naught will not be equal to 0. So you have r square minus n square must be equal to 0. So your r must be plus or minus n. Okay, the first one is r must be plus or minus n. Okay, the second term, look at the second term. The second coefficient k equal to 1. So you have a1 1 plus r whole square minus n square. Okay, x equal to 0. And this term already just now we have denoted as r square equal to plus or minus r square equal to n square. So r equal to plus or minus n. So this term should not be equal to 0 because already we know that r square equal to n square. So r equal to plus or minus n. So only possibility is a1 must be equal to 0. That cannot be equal to 0. So it implies clearly that A1 equals to 0. Okay. The first coefficient A0 is not equal to 0 because first coefficient will never be equal to 0. Look at the second coefficient A1 equal to 0. If A1 equal to 0, this comes under power series. So A3, A5, A7, A9 must be equal to 0. So all the odd coefficients must be equal to 0. It's very clear. Because we have taken power series. So it implies if A1 equal to 0, it implies that A1 equal to A3 equal to A5 dot everything will be equal to 0. Is it clear what I am saying? Look at this equation. So second coefficients dot. So that will give you this term, that will give you AK equal to minus AK minus 2 divided by K plus R whole square minus. Is it clear? So what is this one? This is recursion formula. So which we have studied earlier for Legendre polynomials. So this is the recursion. So recursion formula or relation. Okay. Correct. So in the last class, Legendre polynomial, we obtained recursion formula, recursion relation. It's a different one, and here it is entirely different. So AK equal to minus AK minus 2 divided by K plus R whole square minus. Substitute now K equal to 2. If K equal to 2, AK becomes A2 equal to minus A0 divided by. So this I can write this as K plus R plus N, K plus R, correct? So now R becomes when R equal to plus or minus N. So in the first case 1, R equal to N. Okay. So when R equal to N, it becomes N and gets cancelled. We have K alone. Okay. Here this becomes K plus 2N. Okay, K plus 2N. Already we are going to substitute K equal to 2. So this becomes 2K plus 2 is right. K into. So this becomes correct. Say R equal to N, K equal to 2. So this becomes K plus 2N, and if you substitute N will cancel, you have K alone. So K into K plus 2N. When K equal to 2, it becomes 2 into K plus S. Okay. Where for A4, this becomes, this becomes A4, this becomes clear. Doubt is out. Come on, anybody is there? Doubt there? Okay. So this must be A4 divided by 4. Correct? 4 plus. Okay. So I can write this as 2 square. Okay, 2 to the power 1, 2 square. So similarly, A6 it will be, and this can be simplified as A0 divided by, if you substitute for A2, it becomes 2 to the power 1, 2 square, 4 plus 2N, 2 plus. Okay. So similarly A6 becomes, A6 becomes minus A0 divided by 2 to the power 1. One mistake we have made. So this becomes, yes, because already we have minus A0. So this must be minus A0 to 2 square to 2. Yeah, you are correct. Then it becomes 6 plus 2N, 4 plus 2N, 2 plus. using these coefficients we can form a series using this solution. Okay, can we do it? So we have the solution y equal to sigma a x to the power k plus r. Of course we have substituted r equal to plus here. So this becomes I have, because a naught is a common term, I can pull a naught out, correct? And x to the power n also out, correct? X to the power n also out. Remaining term will be x to the power k, ak x to the power k. Okay, so ak x to the power k. And of course a naught we can substitute a2, a1 and all those things. So first term will be your a naught alone. So 1, first term. If you substitute k equal to 0, the first term will be 1. A naught into x to the power n. The second term a1 will be 0. So we are not going to take all odd series out. We are not going to take. We are going to take only even series. So this must be a2, a4, a6 goes on. What about my a2? A2 is this one. So you have minus 9 x square, correct? X square. The remaining term will be 2 to the power 1. 2 plus 3. The next term will be plus x to the power 4, correct? Come on. X to the power 4. This term will be 2 to the power 1. Because sign changes, I am going to write this as, okay, so minus 1 square minus 1 to the power. So sign changes. So 2 to the power square. So this becomes 4 plus 2 plus dot. The next term will be a6. The last term will be minus 1 to the power k. The last term, for example, here k equal to 0, k equal to 1, 2, 3. Because 1, 3, 5 and all we are not going to use. Only we are going to use 0, 2, 4, all those things. So the last term let it be as k. So this becomes minus 1 to the power k, x to the power. See, look at this 2, 4. So it must be 2k. Is it clear? Okay. It must be 2k divided by. You have 2 to the power 1, 2 square. Next term will be 2 to the power. 2 to the power goes on. So you will have 2 to the power 2k. I can pull here 2 out. Here also I can pull 2 out. So this will become 2, 3, 4 goes on. So it becomes k factorial. The remaining term will be n plus 1. Because we have pulled out, okay, 2 out. So n plus 1. We have pulled here also 2 out, here also 2 out. So n plus 1, n plus 2. Is it clear what I am saying? You can pull n plus 2 out. So you can pull 2 out. So that will give you n plus 1. You can pull 2 out. So that will give you 2 n plus 2. So dot. So you will have n plus 2. Is it clear what I am saying? Minus 1 to the power bigger. Big. So here must be, you know, 2. Okay. So you will have the last time is this one. So you have a naught x to the power n minus 1. So you can pull this term out. So this is a naught x to the power n. Okay. I can write this as minus 1 to the power k. I tell you why it is so. The remaining term will be we have x to the power 2k. The last term I'm going to write. So this becomes a series. Okay. Last term. So this becomes 2 to the power 2k. Okay. K factorial. K factorial. N plus 1, n plus 2, dot, n plus k. Okay. So you have n plus 1, dot, n plus k. I am going to define I'm going to define A naught as 1 divided by 2 to the power n gamma 1 plus n. So it's a definition for my A naught. Okay, I'm going to define A naught gamma 1 by 2 to the power n gamma 1 plus n. So I'm going to substitute this. So we will substitute. So this becomes minus 1 to the power a. Okay, x to the power n divided by 2 to the power n gamma 1 plus n. So I have substituted. So remaining term will be x to the power 2k summation, let it be summation. I will 1 minute. So this becomes 2 to the power 2k k factorial n plus 1 dot dot dot. Okay. Now from gamma equation we know already gamma 1 plus n equal to n into gamma n. We know from gamma integral, beta integral, beta function and gamma function, we know gamma 1 plus n equal to n. So I'm going to add 1. So this becomes 2 plus n. So this becomes n plus 1 gamma n plus 1. Okay. I'm going to add 1. So this becomes n plus 1 into gamma n. So similarly, gamma 3 plus n becomes n plus 2 gamma n plus 2. Inside n plus 2 I can substitute this one. Okay. So this becomes n plus 2 n plus 1 gamma n plus 2. Okay. Similarly, I can write gamma k plus n plus 1. Okay. K plus n plus 1. So it becomes n plus 2 or n plus 1. Last term will be n plus k gamma n plus 1. Last term will be always same, n plus 1. The previous term also n plus 1, everything will be same. So this term, this will be dot dot dot. Okay. So you have to start from n plus k, then n plus k minus 1, dot dot dot, n plus 2, n plus 1, then gamma n plus 1. So look at this equation. N plus 1, n plus 2, n plus k into gamma n plus 1. I can replace this as gamma k plus n plus 1. Second factor will be x to the power 2k. Here 2 to the power n is here. Here I can write this as x to the power n plus 2k. Correct? X to the power n plus 2k divided by 2 to the power n is there, 1 2k is there. So this term can be written as minus 1 to the power a. Okay. X by 2 to the power n plus 2. Okay, n plus 2k divided by n factorial. This n factorial, sorry, k factorial multiplied by you have gamma k plus n plus 1. So this will be your Bessel function. This is your Bessel function which is denoted as j n of x. So we have obtained only one solution. Okay, this is one solution, and j n of x, this is equal to minus 1 to the power. Of course, we have summation here, and here we have summation here. Okay, we have written summation now, so here it's okay. So you have minus 1 to the power a, x by 2, n plus 2k divided by a factorial gamma n plus a plus 1. Okay, so this will be your j Bessel function of first kind. So this is your Bessel function of. Okay, so now we can write